All right, guys, today we are going to take a look at two items, one of which we've already taken a look at, mean value theorem for integrals, which we called average value. The next one will be second fundamental theorem of calculus, so that's going to be our new one. But first, let's just kind of go back over average value. This one is technically called mean value theorem for integrals, but I think that makes it a little bit difficult in remembering which one we're working with because we do have a mean value theorem for derivatives. So I usually refer to this one as average value because that's pretty much always how they ask the question. Remember to find the average value of a function on the interval a to b. We take 1 over b minus a times the integral from a to b of the function. Okay, we did this before, but let's go over an example, make sure we got it. Let's say we have the function f of x equals 3x squared minus 2x, and we want to find the average value of this function on the interval 1 to 4. Okay, so let's take 1 over b minus a, 1 over 4 minus 1, times the integral from 1 to 4 of the function 3x squared minus 2x, x. 1 over 4 minus 1 becomes 1/3. Integral of 3x squared becomes x cubed. Integral of 2x becomes x squared. And we're evaluating from 1 to 4. Let's plug in 4 first. Okay, we have 4 cubed minus 4 squared minus, now we plug in 1. 1 cubed minus 1 squared. We like when we have that. 1 minus 1 is 0. So now we're simplifying here. 4 cubed is 64, minus 4 squared is 16. 64 minus 16 is 48, divided by 3 is 16. So the average value of this function, f of x, on the interval 1 to 4 is 16. Okay, let's do one more. Let's do a trig problem. Let's say we want to find the average value of the function, let's see, 2 secant squared of x on the interval negative pi over 4, pi over 4. So 1 over b minus a, 1 over pi over 4 minus negative pi over 4, times the integral from a to b, integral from negative pi over 4 to pi over 4 of the function. All right, pi over 4 minus negative pi over 4, that's going to become a plus. So that's 2 pi over 4, which is pi over 2 on the bottom. So if we have 1 over pi over 2 and we flip and multiply, that gives us, what I say, 1 over pi over 2, that gives us 2 over pi. Now let's take a look at the integral. Integral of 2 secant squared is going to become 2 tangent. And we want to evaluate at our limits of integration. So if we plug in, we have 2 over pi out front, 2 times tangent of pi over 4, minus 2 times tangent of negative pi over 4. Okay, so we have 2 over pi times tangent of pi over 4 is 1, tangent of negative pi over 4 is negative 1. So we have 2 minus a negative 2, so plus 2. That means we have 2 over pi times 4, which would be 8 over pi. So the average value of f of x equals 2 secant squared of x on the interval negative pi over 4 to pi over 4 is 8 over pi. Okay, again, that's something we've already done, but I did want to revisit. That's just like a definite integral with the extra piece of adding on multiplying by 1 over b minus a at the beginning of the integral. All right, next big one for today. the second fundamental theorem of calculus, which we can abbreviate as FTC. Remember, that is an accepted abbreviation. So second fundamental theorem of calculus, there's two versions of this. Okay, so I'm going to talk about each one. Integral, the derivative of the integral from a to x of f of t dt equals f of x. Okay, so here's what you want to think about. A is just any number. A is a constant. So any number. The integral from any number to x. Okay, we're going to take the derivative of that. Think about what we're doing. If we're taking the derivative of an integral, we're going to get the same function back. The difference may be if we had a constant or if we had something other than x. So this one is very easy. All we have to do is plug in x for the t values in the original function. Okay, if we have, for example, the second version, integral, derivative of the integral from a to g of x, so where g is a function of x, of f of t dt. For that one, we end up with f of g of x times g prime of x. And now notice that looks just like your chain rule. The reason for that being, now we're plugging in some kind of function of x. So if we were to do that, whenever we took an integral, when we take a derivative again, we still have to think about chain rule. We have to take the derivative using that chain rule and multiply by the derivative of whatever is inside the function. All right, if you're sitting here confused about this, don't worry. Let's take a look at a couple of examples. We'll do a couple easy ones and a couple more difficult. Let's start with an easy one. Let's say we want to find the derivative of the integral from 0 to x of square root of t squared plus 1 dt. All right. If we're finding the derivative of the integral, notice the integral is only to x, right? So that's that first case. All we have to do is plug in x into the original function. Done. Another way I've seen these worded before, sometimes they'll tell you, and they usually use a capital F, if f of x equals, let's say, something pretty simple. Maybe it's integral from 2 to x of t squared dt. Find, find f prime of x. So we're doing the same thing. We're taking the derivative of an integral. Then the derivative of the integral is going to be this function with x plugged in because we're only going to x. Okay. Now, those are really easy. Almost too easy. Almost so easy that you think that this couldn't be real. Let's take a look at some of the more difficult ones with a function that we're going to. So let's say we have the derivative of the integral from -2 to x squared of the square root of t cubed plus 4 dt. Okay, so here's the difference. Notice that this has an upper limit of x squared. That's not just an x, so this is the function. We have to take, we're taking derivative of an integral, so we still want to start the same way. We want to plug in this upper limit of integration, this x squared, in place of the t. So if we have x squared all cubed, that's x to the 6th, and we still have plus 4. Now, the big thing we have to remember, we have to multiply by g prime, the derivative of this upper function. Derivative of x squared is 2x. And we're done. Let's try another one. We'll do some trig this time. Okay, but not quite what you think, maybe. Let's try one of these where we're told f of x is the integral from 5 to cosine of x of t squared dt. and we want to find f prime of x. Okay, well, we know that we're taking the derivative of the integral, so we're using second fundamental theorem, which says we need to plug this function in for the t. So we're going to have a cosine squared of x. But then, because this is not just an x as our upper limit, we have to remember to multiply by derivative of that function. So derivative of cosine is negative sine. So I'm going to put a negative out front. So f prime of x would be negative cosine squared of x times sine of x. Let's try one more like that. Oops. Say f of x is the integral from pi over 2 to x cubed. Oh, excuse me, pi over 3. Well, that looks terrible. Okay, so pi over 3 to x cubed of cosine of t dt. And we want to find f prime of x. Okay, again, think about what we're doing. We're taking derivative of the integral. So we're using second fundamental theorem. We do not have just a plain x. We have an x cubed up here. So we want to start by plugging in for the t. So we will have cosine of x cubed instead of cosine of t. And then we have to remember to multiply by the derivative of this upper function. So derivative of x cubed is 3x squared. So f prime of x is 3x squared times cosine of x cubed. Okay. Usually you see these as part of a multiple choice question. A lot of times it'll look similar to this, but instead of saying find f prime of x, it'll say maybe like find f prime of pi, something like that. Okay, or find f prime of a number. So you have to realize how to find the derivative function, and then you have to be able to plug in a value. Okay, it's a quick way for them to tell if you understand what second fundamental theorem says, and also can you evaluate.